Okay, so welcome back to the lecture, and today we'll be just solving our very own problem. And this problem, as you know, is a representative or a toy version of any such problem. So I've got a grid like this. All I have to do is to find a path from a source all the way up to a goal with some obstacles, in general any state space. The only change that I have now is that my actions are stochastic. And what that means is, suppose I am at 1, 1 over here and I apply the action right. Of course, I should go to 1, which is this one. But sometimes what happens is that if I apply it a number of times, sometimes I, instead of a 2, 1, reach a 1, 2, or the robot by chance slips. It could happen in any state space. And we'll see what do we do about such a problem. And luckily we have looked into these cases when we were playing game against nature. So the expecting minimax algorithm, when there are only two players, yourself and God, you take action, God makes you slips, becomes the expecting max algorithm, and that algorithm gives me a policy. So this is what is called as a policy, which means I get at state S, which is the best action. So it could be up, down, right, left, like it appears to me that at 1, 1, if I really need to reach the goal, the best action should be a right so that I can go. Sometimes I'll slip, but I'll see what to do. And because it has already been covered, I can straight away get into the business and say what things we will do it in a different manner. Now, games are different. You've got exactly one source, every game starts at that point of time, and repetitions rarely happen, so you can go with a heuristic expansion of a game tree. Of course, in discussion sessions, most of you pointed problems, and we were generating the entire tree with alpha beta pruning, but we could be more heuristic about it. Now we are dealing with problems where too many states will be repeated. So 2, 1, I take an action left, I go here, which is a repeated states. That's not what was more commonly happening in two games. Or to say that now I'll try to solve the problem in a completely mathematical manner, and by solving it in a mathematical manner, I'll see what can I get. So let's have a few definitions now for this specific modeling. The first is, of course, where I define my probability. So actions are stochastic. That means now I will have in some probabilities. Let me give a definition first. So PS dash given SA is the probability of reaching the state S dash given that agent applies action A at the preceding state S. Complicated, of course, I will simplify that up immediately. As of now, I've defined in probabilities. So what's the probability of reaching a state given I know my previous state and my previous action? It's also called as the transition probabilities. And it is also denoted by a term which is TSAS dash. From S, I applied action A and reached the state S dash. And it's also called as a model. Now remember, the model is a generic term. It represents many things. What's the physics by which the agent is moving? What is the environment and all its assumptions? They're all called as model, and we shouldn't be using very generic names in our specific definitions. But the moment I get a term which can have two meanings, then I'll say that okay, we use specific meanings. As of now, it will be called as the model because we don't have any other meaning right now. So transition probability is the same as probabilities of motion. It is the same as the model. And as I said, I'll simplify it up. So let us say that the world is extremely small like this, and the agent is currently at 2, and for reasons we do not know, the agent says that I will take the action up. Maybe there's a goal, maybe somebody told that's the optimal policy. And now I say that the agent does move up. However, that happens only with a probability of 0.8. So I'll say the probability that the agent goes to the correct state 2-3, given it is currently at state 2-2 and apply the action up, is equal to 0.8. And as we know, it can slip. So there's a 10% chance it slips here, and there's a 10% chance that it slips here. So similarly, probability of going through 1-2 given at 2-2, comma up is equal to 0.1, and probability of 3-2 given from 2-2, I take the action up, is equal to 0.1. The probability that I go to any xy if xy is not equal to 3 and xy is not equal to 1-2 and xy is not equal to 3-2. So the summation of all probabilities is of course 0.8 plus 0.1 plus 0.1, which is a 1. And we know it by the probability theory as well, that summation of probability of S dash given SA should be always equal to 1. Now the interesting aspect of it comes over here, because without telling you, I did make an assumption. So in general, let's say the agent was at a state S0 initially at time 0. The agent applied an action A1, it reached S1, then applied the action A2, reached S2, then applied the action A3, reached S3, all the way up to apply the action AT and reached ST. And what I do say is that I need to find out what after that, if the agent applies the action A and reaches S dash, I need to find out the probability of reaching S dash given all these things. I always know my history. Given S0, given A1, given S1, given A2, given S2, given AT, given ST. This is what I need to find out. So why did I say that everything else doesn't matter? Only thing that matters is which was your last state and which was your last action. This has a famous name and this is called as the Markovian assumption. So the Markovian assumption says that the probability of reaching here from here only depends upon from where did I go and which action did I apply. It does not depend upon how did I come here, like this, like this, like this, like this, like this. It only depends upon my current state and my current action. It does not depend upon the history. It does not depend on how did you reach this particular state, and that is what is called as a Markovian assumption. So the probability in going to 2 3 from 2 2 given the action up was applied is only dependent on 2 2 and up. It's not dependent on how did you reach 2 2. Histories don't matter. I do this, otherwise it will become a computationally extremely difficult problem to solve. And now let me just, instead of action up, also take in the other actions which are possible. So very quickly, just writing down the modeling. So I say instead of up, I take a right. So with 10% I go to 2 3 and with a 10% I go to 2 1. So probability of going to 3 2 given from 2 2 you applied a right is equal to 0.8. Probability in going to 3 given from 2 2 you applied the action right is equal to 0.1. Probabilities need to add up to 1. So of course the probability in going to 1 given from 2 2 you applied the action right is also 0.1. And similarly you could do it for the down. So from 2 2 if you apply down, the probability in going to 1 will be 0.8, 1 2 will be 0.1, 3 2 will be 0.1. Left, the probability in reaching 1 2 will be 0.8, 2 3 will be 0.1 and 2 1 will of course be 0.1. So I've defined my probabilities. Now let's try to see if we can define what our solution should be. So in order to model the problem completely, I will define something which is called as the reward. So the reward is the immediate, so reward is the immediate feedback. It can be positive or negative given by the environment to the agent so as to indicate to the agent if the last motion in going to S dash from S on application of the action A was good, and to what extent it was good. So In general, I will define it either as RSAS dash. What is the reward that I get in going from the state S by applying an action A to the state S dash, or sometimes the reward is only a function of the states. It has nothing to do with from which state did you go and what action did you apply. So it's sometimes just RS. So let us define in the rewards also for that problem. So again, I take a miniature problem. It goes like this. And this time I start over from 1, 1, and I have an obstacle. So suppose from 1, 1, I apply the action right, I did not slip, and I reached 1, 2. So I say the reward is equal to minus 0.1. Why minus 0.1? Because my legs will ache a little bit. Legs will ache a little bit, so I'm saying that it wasn't very pleasing that I took a step and my leg started aching. So I say the reward in going from 1, 1 on the action right to 1, 2 is equal to minus 0.1. Otherwise, I say the reward in going to 1, 2 is equal to minus 0.1, whichever way you say. However, sometimes what can happen is from 1, 1, I do take a right. However, this time I collide, and of course, it's not that you will reach 1, 2. You won't reach here. After collision, you will stay as it is over here. So I say 1, 1, and I write that I collide. So I say the reward in going from 1, 1 by the action right, staying at 1, 1 with a collision, of course, is equal to minus 1000. Very bad. You collide. Absolutely bad. And let me take in another example. Let's say this was the goal. So I am at 2, 3. 2, 3. I took the action right. I did not slip. I went to 3, 3, which by the way was the goal. So goal reached. So the reward for this is plus 10,000. I'm very happy I reached the goal. No more worries into life. So from 2, 3, I take the action right. I reach the goal. The reward is plus 10,000. I'm very happy I reached the goal, which is what you would be when you pass the AI course and you'll be done. So you reach the goal, you're happy, it's a plus 10,000 reward.